Good morning, everyone. Today I have a pleasure to present our invited speaker, Dr. Jasimuddin Ahmed. Dr. Ahmed is Assistant Professor of the Department of Chemistry in Jadavpur University, India. Today, he will talk about the development of organic single electron transfer catalysis for CC cross-coupling reaction. Before to present, give to Dr. Ahmed to talk, I want to tell a little how is the professional experience of him. He did postdoctoral research in the Department of Chemistry of University of Texas at San Antonio with Dr. Oleg Larionov. Also, he did a research associated in the Department of Chemical Science, Indian Institute of Science, Education and Research, Kolkata, India. He started his career doing a Bachelor of Science in the University of Bourgogne, India. Also, he did a Master of Science in the Indian Institute of Science, Education and Research, Kolkata, and also he did his PhD in this institution. I also have to mention a select publication that he did with Dr. Mandel in Chemical Review that has a good impact factor. Welcome to Dr. Ahmed. Thank you so much to stay here because for Indica it is so important to know about your topic. Now we are pleasure to hear your presentation.
Thank you very much, Dr. Johan and Dr. Cameos for introducing me and giving me this nice platform to present my research. So today, basically, I chose a very interesting topic. So this is basically like a trade. So in the development of CC cross-coupling reactions. So here what I'll be talking about today. So how the CC cross-coupling reaction is, how much important it is, and how we need to develop this in much cost-effective and much inexpensive as well as very easy accessible process. So my journey, I can say this is a larger part of my PhD. Basically, I focused on that. So because this was like a journey on the development of CC cross-coupling reaction without using any transition metal. So this story was basically based on this development of organic single electron transfer catalysts for CC cross-coupling reactions. So with this, we know what is CC cross-coupling reaction, but still I'm just briefly introducing what is CC cross-coupling reaction. So CC cross-coupling reaction is actually formation of two different carbon bond between two different carbon of two different substrates. So suppose C1X and C2Y, and we are forming C2 and C1 and C2 a new bond. So that is basically a CC cross-coupling reactions. So what is the importance? Why do we need to perform this reaction? The importance is that it is very useful tool to prepare different biologically active molecules, agrochemicals to materials to drug and medicinally important molecules. And you can see like boscalides as well as different OLEG based molecules. Here you have a very important process involved in the preparation of big molecule, that is the CC cross-coupling reactions. So far, what we know for the preparation of this CC new bond. So we know these traditional methods using palladium-based catalyst, which was a pioneering development by Suzuki Miura cross-coupling, is a very pioneering development on this CC cross-coupling reaction using palladium catalyst. And also some other coupling, CC cross-coupling of different alkenes also introduced by Hay. And in 2010, it was really recognized by Nobel Prize to the Hague, Negishi, and Suzuki. So here, if you see Suzuki cross-coupling reaction, it needs a special functionalization like aryl boronic acid. In case of Stille coupling, you need a team-based functionalization, as well as for the Negishi coupling, you need a zinc-based functionalized aryl partner along with some aryl halide. In presence of palladium catalyst, you can get access of CC new biaryl product with a new CC bond. What is the problem of this molecule? Although this is very robust, and I think this is the most useful method for this CC cross-coupling reaction, but the problem is here that you need, okay. So you need palladium as well as specially functionalized aryl partner. So my first target was to avoid special functionalization. So this is not me. I am introducing first time that let's avoid the special functionalization. It was first introduced by Fognau. Professor Fognau came up with a very new and really great idea that if you take a activated CH bond of a arene or heteroarene partner, and if you take aryl halide in presence of the palladium catalyst, with high temperature, we can get access of biaryls with this new CC bond through the new CC bond formation. And followed by that, Itami and different famous organic chemists like Darcel, Dowsett, Dixnop, Gripo, they actually developed in this field for the direct CH arylation reaction. So here, when I was the beginner in my PhD lab, so there actually I was assigned to develop something in this era. So in this field, I came up with a palladium-based dimer, which was supported with a abnormal carbene, which called abnormal carbene, which was originated by Guy Bertrand from UC Riverside, and we use this ligand to support the palladium-based this dimer, and we use this catalyst to activate different aryl chloride to do direct CH arylation of different heteroarenes. You can see like furan, thiophene, N-methylpyrrole as well as indole. We could do C2 as well as C3 arylation successfully. But here still we need palladium. So our focus was we need to actually avoid palladium because it's expensive and rare. So Itami in 2008, Professor Itami came up with a great idea that let's use this concept of direct CH arylation and let's tune different ligand like content phenanthroline to prime bipyridine based ligand in presence of a high equivalent of potassium tarbutoxide that is a strong base with the high temperature, and successfully they could report biaryls at this condition. And followed by this work, Shi and Qualkers, Lei and our Lee, they also introduced Morphy. They introduced different processes and different ligands to perform this biaryl formation. So here the concept was to generate some in situ radical initiator. Now the radical initiator will transfer electron to the aryl halide to generate aryl radical, and now this aryl radical will attack to the arene center, which followed by proton abstraction, it will give a radical anionic biaryl intermediate, and now this after the electron liberation, it will give you the stable biaryl product. So if you just demask this process, you will see like electron is coming to the catalytic cycle, and at the end of the product formation, again you are gaining electron. So it looks like electron is playing role of a catalyst. And this was nicely introduced and described by Studer and Curran in 2014 in Nature Chemistry. So they described that electron is a catalyst. So that is a really nice article and really useful and conceptual. So with this, we could understand what is the mechanism, what is the conceptual background for this kind of designing, but still this process is suffering from certain things. You need high ligand loading, like 20 to 30. So it's not exactly a catalytic method, it's like a semi-stoichiometric method. And another thing is that you need high temperature and there was a limited substrate scope in terms of the arene partners. So with that, our focus was to develop a catalytic CH annihilation at room temperature without using any transition metal or any other external stimuli. So indeed, in this goal, keeping in our mind, we strategize our methodology, and we thought of a new molecule, that is a phenylenyl molecule. So that is not new. I should not say it's new. It's very old and very well known from last 60 years, but it is well known from a different background, from the material science. By Haddon or Reid, they introduced this molecule in 1958 and 1975. So this is like a smallest word alternate hydrocarbon present in a graphene sheet. So this is the phenylenyl molecule. This on the smallest part, the word alternate smallest molecule of the graphene sheet available. So what is the specialty of this molecule? If you take phenylene, then if you treat with the DDQ, you will end up with a phenylenyl cation. Now, as the phenylenyl made of 13 carbon atom, so you will end up with 6 bonding, 6 anti-bonding, along with it will give you a non-bonding, empty non-bonding orbital with 12 pi electron system. So now if you give an electron, first it will accommodate in the non-bonding orbital. So the speciality of this molecule is that if you give an electron, it will go locate to the non-bonding orbital. And as we know that if you give electron to the non-bonding orbital, it will not really affect too much to the structural stability of this molecule. So not only one electron push, you can give 2 electron injection, and the both electron it can accommodate in the non-bonding orbital without disturbing its aromaticity as well as its stability. So Zhang et al. In 2017 came up with very nice observation and calculation to see that it's true that if you give electron consecutively up to 2, you will not really lose the aromaticity of individual benzene ring of phenylenyl molecule. Here, let me tell, NICS is nuclear independent chemical shift value. So this value, if you see, it's negative, like 17.2 for the cationic one. This high negative value actually indicates high aromaticity. Low negative value indicates low aromaticity, but still it's aromatic. So you can see upon the first electron injection, second electron injection, you can actually preserve the aromaticity, although the aromaticity is decreasing. So it is actually indicating that no, the concept is really well, and it was well proved and well thought. But so far, this molecule was only introduced in the material science. But our focus was to use this molecule in the catalyst designing. So we use this molecule as a single electron transfer catalyst to perform the CC cross coupling reaction. So at first, we use this molecule, you can see this kind of phenylenyl based ligand, and we took potassium terbutaoxide only 10 mole % with 5 mole % of the ligand loading. We took different activated CH containing heteroarenes, and we could actually get access of biaryls at room temperature without any external stimuli. And with this methodology, we could actually get access of different biaryls of using direct CH annihilation of thiazoles, benzoxazole, as well as different substituted benzoxazole. Not only that, we also could do direct CH annihilation of thiophene, furan, so with moderate to good yield. So not only that, we also could modify our process to do the direct CH annihilation of pyridine with the simple modification by the pre-treatment of HDF4 to the pyridine to block the lone pair of nitrogen and enhance the acidity of the C2 proton of pyridine. So with this method, we could do the pyridine annihilation, C2 annihilation, and we could also utilize this method to prepare gram scale from some biologically active molecule, large scale preparation for some biologically active molecules core part. So with that, let me conclude this part. Like we could develop first time a transition metal free room temperature arene annihilation with satisfactory yield, and we did a thorough mechanistic understanding, a thorough mechanistic investigation to understand what is the exact catalyst involved in this reaction, and we could characterize the trapped catalyst in situ in the reaction mixture by the crystallograph. So what is the limitation of this work? The limitation is that if you notice, we could only perform direct CH relation of heteroarenes where the CH is really activated. So we need to think about what about simple arenes like benzene, toluene, or anisole, something like that. So here the problem is that if you really want to design a direct CH relation reaction for a electronically unbiased arenes, then the problem is that here proton for benzene is less acidic in terms of the heteroarene like thiophene. And another thing is the carbon atom is less electrophilic than that of the thiophene. So the aryl radical attack is not that much favorable, and the proton obstruction is not also favorable. So here only aryl radical generation from the one coupling partner is not the only one. You have to deal with the activation of another substrate as well. So you need to now tune both the energy of substrate A and substrate B. So with this thought process, we came up with a new catalyst, that is the cationic phenylenediol molecule. This cationic phenylenediol molecule we took 2.5 mole%. We treated with a organic electron donor, that is TDAE, or sometimes we also treated with potassium, elemental potassium in DMSO at room temperature, and we could perform direct CH relation of different arenes with aryl diazoxide salt. And you can see we could perform direct CH relation of benzene, toluene, anisole, nitrobenzene, or sometimes chlorobenzene, benzonitrile, ester containing, as well as we could do mesitylene and trimethoxybenzene as well with good to satisfactory yield. So with that result, actually we were very interested to see what exactly happening in this reaction, that why this cationic phenylenediol is able to perform CH relation of electronically unbiased arene. Then we started investigating the mechanism. We took the cation first, then we treated with TDA, and we got a green colored solution from the yellow colored solution, and we saw the APR measurement actually told us that it is a radical species. And then we took this in situ generated radical and we treated with aryl diazoxide salt, and we got a aryl radical. We're supposed to get a aryl radical, and we treated with a tempo, that is a free radical, and we could trap this aryl radical. Hence, we are proving that this aryl radical, phenylenediol radical, is transferring one electron to aryl diazoxide salt to prepare aryl radical in situ in this reaction. Now we have cationic phenylenediol in our hand. So this is the cationic phenylenediol molecule we have in our hand. So how exactly this cation phenylenediol molecule is activating the other substrate, that is the arene? So we did several spectroscopic measurements to see how actually it is activating the arene partner. So first we took help from different spectroscopic measurement like UV-Vis, fluorescence, as well as lifetime measurement from TCSPC, and we can see when benzene to toluene to mesitylene, with increasing the pi donorability of the arenes, we are actually seeing a significant quenching in the both UV, fluorescence, as well as the lifetime. And you can see from this, you can visualize from this photographically, you can visualize that with increasing the pi donorability, we are actually diminishing the fluorescence character of the phenylenediol cation. So it means the phenylenediol cation is getting quenched by the pi electron of the arene. So not only this kind of UV fluorescence or absorbance spectroscopy, we actually could prove this kind of interaction by the NMR spectroscopy as well. So when we did a NMR spectroscopic measurement of the phenylenediol cation in presence of benzene D6, we saw surprisingly that there is a uphill shift of the phenylenediol cation in presence of the benzene D6. It means the cationic character of the phenylenediol is diminishing. So not only this, we also could do NOE, that is nuclear overhauser effect experiment, and we saw there is a significant resonance of proton of benzene here, He, when we are specifically resonating only one proton of the phenylenyl cation. So this is for benzene. We could also do with the toluene, a mesitylene, and we found the same. It means there is a good binding interaction between the phenylenyl cation and the arenes. So not only the experimental proof, we also did some theoretical investigation. So density functional theory actually helped us to understand the interaction, and we saw from benzene to toluene to mesitylene, the cationic character of the phenylenyl cation is diminishing and the cationic character on the arene is increasing. So that is noticeable. Now we have cationic character on the arene. It means it is directly increasing the acidity of the CH bond, as well as you have a significant electrophilicity in the carbon center of the arene. So with that, we propose that probably this kind of pi-pi dynamic interaction between the phenylenyl cation and the benzene or other arenes we have, which is activating this arene partner. And now with this activated arene partner, we are treating with in situ generated aryl radical, which is forming this kind of radical biaryl intermediate, and which upon proton abstraction and the liberation of HbF4, we are getting bioradical. So this kind of intermediate we also optimize through the DFT, although it is not that convincing. So we really don't know it is really having any interaction with this in this stage or not. So with this, I can say that finally we could actually accomplish direct CH relation of arenes, which was really challenging. So here we could actually reveal that phenylenyl based cation can act as a Lewis acid, pi-Lewis acid to activate the arene, as well as it can act as a redox catalyst to activate the aryl diazoxide salt to generate aryl radical. And finally, I can get access of bioaryls at room temperature without any external stimuli, only in presence of electron donor. So here, so far, what I was talking about two component reaction, like one arene, one aryl halide like aryl diazoxide salt, or some other aryl partner I'm treating and getting bioaryls. So we thought that let's take what is the activity of our catalyst in the three component reaction. So we designed this kind of reaction. We took this kind of reaction where one substrate is styrene, another one is aryl diazoxide salt, another one nucleophile is alcohol, and to get this kind of three component additive product. And in this project, actually, we took the first catalytic protocol where we apply this kind of ligand in presence of potassium tetroxide, and we could do the three component addition in different styrenes in presence of aryl diazoxide salt, and this is the final product. And with that protocol, we could do a good number of substrate with good to satisfactory yield with different electron rich styrenes and different aryl diazoxide salts. So next, we thought to tune what about different alcohols, and you can see in terms of instead of methanol, when we went to ethanol to isopropanol to terbutanol, you can see this three component additive product, the yield of this product is decreasing. So in case of isopropanol is 78, then isopropanol it is 53, then terbutanol it is very low, it is 23. So with increasing the steric bulkiness of the alcohol, we are actually compromising the three component additive product. So we thought, what is happening? So let's do a control experiment without adding any alcohol. So we did that, and we could perform direct CH relation of styrenes, that is the H-type coupling, that is simple Marvin addition reaction. And we could perform this reaction without any alcohol with good to satisfactory yield. So that was a really surprising result to us. And finally, we communicated this result in JOC 2019. And herein, we could report that no, our methodology actually efficient to perform this kind of three component reaction. So far, these three reactions on the CC cross coupling development, we are dealing with aryl diazoxide salt. So as we know, there are several drawbacks of aryl diazoxide salt. First of all, it is not commercially available. And another thing is that it's not so stable. You have to store under freezer, and you have to prepare the aryl diagenum salt from the corresponding anilines. So it is not economically as well as step economically viable, as well as not atom economical process, because you are compromising 2 N2, 1 boron and 4 fluorine. So what can be the remedy? So remedy is that we have to think some process where we can directly use commercially available and cheap aryl halide as the coupling partner. So that was our first goal. As I told, Itami in 2008 introduces direct CH-arylation reaction at high temperature with aryl halides. So we thought how we can strategize our process. So first we took a help from the theoretical study. It's a qualitative diagram. Here I'll be showing. So this is the empty non-morning orbital of this phenylenediol based catalyst, what I'll be dealing with. And this is chlorobenzonitrile. And to this catalyst, so you will end up with a SOMO, and its energy is not high enough to transfer electron to the chlorobenzonitrile. But if you give one more electron, then this W occupied and dianionic phenylenediol based cation dianion actually now can transfer electron to the chlorobenzene. Still, it cannot transfer to the chlorobenzene, but the activated chlorobenzene like chlorobenzonitrile, it can be activated with this dianionic one. And as I introductory slide, as I told, the phenylenediol based cation you can achieve to reduce the means double electron injection in this product. So here, so our first attempt was to develop to understand, is it possible to design this catalyst or not? So theoretically, I can say it is possible, but we have to check theoretically, experimentally, is it possible or not? So what we did, we first took this phenylenediol based ligand, and then we took a same equivalent of potassium tetroxide, and that should be my pre-catalyst trapped with brown ether. And fortunately, we could get the crystal, single crystal, and this is the X-ray structure of this catalyst. And then we took this catalyst, pre-catalyst, we treated with another equivalent of potassium. Here, potassium supposed to transfer one electron, and here you can see from the yellow color, it is transferring to dark green color. And the EPR study is showing there is a radical phenylenediol based radical species. And then our attempt was to crystallize this radical. That will be great if we can crystallize. Unfortunately, we could crystallize this radical anionic species, and we got, this is the hexagonal single crystal of this molecule, and this is the crystallographic structure of the phenylenediol based radical anion. So this was the first phenylenediol based anionic radical with the 13 pi electronic system, where two here almost like phenylenediol is sandwiched between two potassium brown ether unit. So next we started searching what is the fate of doubly reduced species. So we started with the mono-reduced species, that is the radical anion. Then we treated with another equivalent of potassium in presence of brown ether to trap, and we saw that green color is slowly diminishing to and transferring to the chocolate brown color, and the EPS signal is diminishing. It means slowly the radical character is the phenylenediol is losing its radical character. So we thought probably this kind of species forming inside that, and we tried hard to get this crystal structure of this molecule, but unfortunately we could not get. So what we thought, we optimized this kind of structure. The problem is that if you actually try to accommodate 3 crown ether potassium unit in the periphery of the phenylenediol molecule, you can see from the optimized structure, the phenylenediol molecule is getting puckered. So definitely it will not be stable molecule. So due to high sensitivity of this molecule, even under 0.1 ppm, below the 0.1 ppm oxygen level, we could not get the single crystal of this molecule. Then we tried to get a different alternative to characterize the doubly reduced phenylenediol based molecule. So if it is really forming in the reaction mixture, then I should get a trapped product. So what I did, I treated with HCl. Simple, I did acidification of this molecule. So my thought process was in my mind that if it is a two anionic species, doubly anionic species, then 2 proton will be incorporated in the backbone. So we got the product which is in the DEPT. We saw there is 2CH2 in the DEPT spectrum, as well as we can see in the proton spectrum there is 2CH2 unit. So we can propose from here and in the help of mass spectroscopy also that probably this kind of species is forming where 2 proton has been incorporated in the backbone of phenylalanine molecule. It means in situ it was doubly reduced species. So from that we could actually first characterize direduced phenylalanine molecule. So with that proof we actually designed with that proof we thought that is it possible to make this molecule stable and its aromaticity unaltered. Then we did the NICS calculation and we found that in the NICS calculation also doubly reduced species is not totally losing its aromaticity. So I can think of a reversible process between the radical monoradical to the dianionic species. Also I did additionally anisotropy of induced current density plot measurement. Here this yellow plots actually showing that aromaticity is intact. So it's not the yellow plots lobes are not vanishing. It means aromaticity of the individual rings are intact yet even after double reduce. So hence now I can say my aromaticity will be preserved. I can consider that, and with that we designed our catalytic methodology. We took this phenylalanine based catalyst and we took different heteroarenes and arene, and we took aryl chloride. In terms of this, you can see activated aryl chloride, I can get some satisfactory or good yield or moderate yield. But in case of when I went from the chlorobenzenite to chlorovenzene, I could not get a good yield, like it was below 2 to 5% yield. So it means it is not really able to activate the unactivated chlorovenzene. But when I moved to aryl iodide instead of aryl chloride, then I could do a good substrate scope with different heteroarenes and with different aryl halide partner with good to satisfactory yield. So not only that, we also could perform some intramolecular reaction which can give us hydrophenantridine molecules. And here you can see CBr bond activation, and here the CH insertion, CH activation and CBr activation can lead us this kind of dihydrophenantridine molecule. So this is first time transition metal free aryl halide activation at room temperature in CH arylation process, which is directly mimicking the Itamis process which was reported in 2008 without any external stimuli. So with that, now I can summarize this method that we could actually go to LUMO to SOMO, which was able to activate aryl diazoxide salt but not aryl halide. Then we again added another electron. I pushed the energy of this cation which can activate aryl halides to generate aryl radical, and I can get the product. So from 12 electron pi electron system to 13 pi electron system, then 14 pi electron system. So let me summarize the whole story. So here the whole story is like, first we could do direct CH arylation of different heteroarenes with aryl diazoxide salt, and then we modified our methodology to perform direct CH arylation of different arenes, electronically unbiased arene, which we could perform successfully. After that, from 2 component, we moved to 3 component reaction. We also could show that our process is efficient for 3 component reaction as well. And all these 3 developments were done by switching from the 12 electron species to 13 electron, means neutral or cationic to radical. Then we moved to radical to dianionic species, and now this dianionic species we could perform direct CH arylation reaction with aryl halide, which was our ultimate goal, and we could perform all these reactions under transition metal free condition without any external stimuli using this phenylalanine based organic single electron transfer catalyst. So all this story, we actually got an opportunity to write a review on the by focusing whole story of the phenylalanine molecule. There is a larger part of our research and development of this phenylalanine based molecule, and we could summarize and we could convey our message and our concept, our understanding about this molecule in the chemical review in the recent year. So with that, let me thank definitely my supervisor, Professor Sobin K. Mondal in India as a Kolkata. So his guidance and his inspiration is really a supportive mentality helped me to achieve whatever I am today. And my postdoc supervisor, Professor Oleg Villarionov, is a great and inspiring scientist for me. And I also worked there on the development of single electron based catalyst, but those who are unpublished, I could not really bring those in this presentation in San Antonio, USA. And I'm really thankful for my present institution as a Kolkata worker. I was there for around 8 to 9 months. That is a company, silicon-based company, and San Antonio, University of Texas, and definitely Indicasat AIP Panama for giving me this nice platform to present my work and my message about this CC cross-coupling reaction, and definitely Dr. Johan and Camus for arranging such a nice conference and a seminar. This is our small memory as visit to the natural cavern in San Antonio. So that was a great time in San Antonio. So with that, let me show from where I am. Currently, I am in India. So this is Kolkata, that is a western part of Kolkata, which is in the border of Bangladesh. So this Kolkata is known as City of Joy. There is a diverse range of food, fish, mutton, everything you have. It's really, we love food, we love fish. And there are a lot of historical places, including Howrah Bridge, that is a pillarless bridge on the river Ganges. And this is Victoria Memorial, so that made by Queen Victoria in the British Empire. So with that, thank you very much for your kind attention.